Good morning. How are you? All right. So, what is the difference between a precipitant and a supernatant? Well, let's talk about what they are in general. So, first, let's talk about a precipitant. Okay. So, when we talk about the word precipitation, this literally means to form a solid. Okay. So I'll give you a really good example. This is a particular demo that we would do in class. And the demo is going to be lead 2 nitrate plus potassium iodide. These are both clear solutions when you mix them. Okay. And we use the term AQ here to mean aqueous. Okay. Aqueous means that it is a solid dissolved in water. Okay. It doesn't necessarily have to be water, but for what we do in our class, it will always be water. We are not using any other solvents. These are both aqueous. If you remember back to your solubility rules that I gave you last time, the nitrates are always soluble. And this is a salt, which means that if it comes from the far left side of the table and the far right side of the table, this is also going to create a solution as well. Means it'll be dissolved. So kind of this is like your sodium chloride, like your salt water. Okay. So what we do from there is, since both of these are aqueous, we would mix them in a container. So basically what we would do is we would have two different liquids. We'd have a liquid of PbNO32. And we would have a liquid of Ki, and we would mix these into a third container. Okay, or a test tube or whatever. In class, we would actually do this in a test tube, and then we would dry it out. So what happens when you mix these two guys together is you get a solid in the bottom down here. Okay, it's actually a yellow solid. It forms a yellow solid. And the top layer, so this is all yellow. This top layer right here is what we call the supernatant. Okay. The yellow solid is what we call the precipitant. So if you ever mix two solutions together and you get a solid that forms out of it, the solid itself is called the precipitant, and the liquid that sits on top of the solid is called the supernatant. All right. So why would this be important? Okay, why do we need to know this? Why do we need to know this? Let me ask you this question. If you have spaghetti in a boiling pot of water, do you pour the spaghetti down the drain when you pour the water down the drain? Or do you separate it somehow? Of course, the answer to that is we separate it, right? We use a colander, okay? So you pour the spaghetti and the water through the colander. The colander will catch the spaghetti because that's what you want. You don't want the water. The water is just there to, hey, good morning. The water is just there to allow the spaghetti to kind of heat up, right? And be bendable and flexible. And we put water in the spaghetti, which makes it from hard to soft. But the colander catches it. This is another way of doing some type of filtration. So, or getting two different types of products. Now the question is, which product will be the yellow solid and which product will be the supernatant? Well, what we have to do here is we do this, okay? So basically what you do is you take your two products, or you take your two reactants, and you break them apart, okay? So we're going to draw a circle. The circle represents the reaction container, okay? So this guy right here is the same as the reaction container. We're just looking at this from the top view, okay? This is the top view. So imagine if you kind of poured them in together, right? You poured both of them into the top view. So now we have a solution in here. We're looking down at the container, all right? So what we're going to do is we're going to take our lead nitrate, and we're going to break our lead nitrate across. Now, when we do that, all you do is you take the number and you trace the number back up to the top. And this works most of the time. Sometimes it doesn't work because, as you guys know, the transition metal... excuse me. As you guys know, the transition metals can have varying amounts of charges. As a matter of fact, lead can be a +2 or a +4. So you take that, you take the number 2 and you put it up here, which gives me a charge of Pb2+. And you take the 1 and you put the 1 up here for the nitrate. And that's going to give me nitrate is a -1. All right. And so what happens is that when these guys actually switch places, they retain their charge. So you write down Pb2+ and NO3-. Okay. The other one, we do the exact same thing with K and I. K and I, there's only one of each, which means that this has to be a +1 and this has to be a -1. So write K+ and I-. Now, what do we do now? Well, imagine it this way, right? If you mix two chemicals together and you don't see any color change, nothing heats up, nothing happens, chances are pretty good that these two simply don't mix at all, right? But in this case, we know it mixes, and we know that we get a different compound than what we started with because we got a solid out of this reaction. As a matter of fact, it was a yellow solid. And the top layer doesn't even mix in with the yellow solid, okay? It actually kind of sits on top of it. So what does that mean? That means that we have formed a new compound. And that's the whole point of chemical reactions, is to take something that wasn't there before and to produce something new. So what we do is we take our arrows and we will cross our arrows. So Pb2+ mixes with I- now, and K+ mixes with NO3-. Now, why is that the case? Why is that the case? What can I not do? I can't mix my positives, right? That's not going to happen. I can't mix my negatives because they repel as well. Morning, Bao. Or Han, sorry. I can't remix my positives and negatives of potassium iodide because that's what I started with, and I know that I got something new down here. So that's not going to work. And Pb2+ KNO3-, same situation here. That's not going to work either. So the only possible solution is to actually take the positive on one and mix it with the negative on the other, and we're literally just crisscrossing them. Okay? So that means that when we do this, we can actually form a new set of compounds. Okay? So let me turn this page sideways, and I'm going to rewrite this exact same formula. Okay? So we have Pb NO32 plus Ki yields now, right? Yields Pb2+ and Ki-. Okay? So Pb2+ and I-. So I'm going to cross them. I get Pb, I-, the 1 comes down, so it just gives me a 1. And then I gets a 2, so the 2 comes down here. So I form PbI2 plus, okay, the other one is going to be K+ and NO3-. All right? So I get K+ and NO3-. The positive and the negative will cancel. So I get KNO3. Now, here's the question, though, right? So we know that we formed a solid because we actually did the real experiment, right? So because we formed a solid, then we should be able to look at our solubility rules and determine, okay, what solid is it? So here's our solubility rules, right? So it says PbNO32 plus Ki. So we're looking at these two products over here, Pb and I2, okay? So I-, all chlorine, bromine, iodine salts are soluble, okay? They are soluble. However, it says a rule above that, all silver, lead, and mercury salts are insoluble. So because this is higher in the order, this is the case. And I will tell you this, that is true. Lead, for the most part, is going to form solid. So if you see a colorful solid liquid or solid, mix it with other liquids, probably going to be silver, lead, or mercury. And 66% of the time or so, you're going to end up with something that's really dangerous, like the mercury or the lead, not the silver. Silver is usually a lot shinier. Okay? So that means that because silver, lead, and mercury are insoluble, this is our yellow solid. Okay? This is our yellow solid. And from there, we can look at the other one, which is potassium nitrate, and determine, okay, that must be the clear solution based off of process of elimination. So K and NO3, all sodium, potassium, and ammonium compounds or salts are soluble. So this is our AQ. That means that this is the supernatant. It's the liquid that sits on top of the precipitant. Okay? Now, what does this reaction look like? Well, let's take a look at what the reaction looks like. This is pretty cool.
In the double displacement reaction of lead nitrate and potassium iodide, we have a colorless solution of lead nitrate. We'll add a colorless solution of potassium iodide. As the potassium iodide reacts with the lead nitrate,
they do that way too fast.
Formation of a bright yellow solid, which is lead iodide.
Okay, so they should have done it a lot slower. Do you guys see that? So if you barely drip it in there, which is what they should have done, they should have used like a dropper. If you barely drip it in there, you guys can actually see that that mixes into a solid. Now, over time, what happens is this, okay? Is you get a solid that actually forms. It literally forms a solid out of this. Here's a better one. Look at that one. Okay? So you can see where they're starting to drop it in here. Nothing's happening yet. And then all of a sudden you start seeing the yellow form. Okay? And when the yellow forms, that's ultimately where we get these yellow solution and eventually to that. It should form a solid. Yeah, kind of like this one right here. Okay? Like that. All right? So you guys see how it's kind of coming down in chunks? All right? Those are flakes of actual solid of potassium. I'm sorry, of lead iodide, lead 2 iodide. And so back in the day, this is how they actually used to make paint. So they would make these pigments. This was actually a paint pigment. There's an old rumor out there, I think a wise tale, that Napoleon Bonaparte, who is the one of the main generals, or the main general in France, I think in the 1800s, he actually died of lead poisoning. And it was believed that he actually ingested something like 10,000 times the amount of lead that he was supposed to have, because his entire house was painted with it. And so that's an interesting situation there. I've heard that that's been disproved, but it's definitely an interesting story. Okay. All right. So let's take a look back down our notes here. Okay. There we go. All right. So I'm going to do a couple example problems with you just to make sure that you can understand and actually apply the solubility rules, because that's the hardest part. If you can do this and mix the chemicals together and actually get this on paper, then you can definitely do it in a lab. All right. So let me talk about this real quick. All right, let's come up with another one. We're going to make some silver. We're going to make silver. Let's go with silver fluoride. So silver fluoride as an aqueous solution plus sodium carbonate. Okay. So those are your two solutions, okay, that you mix. All right. Now, before we determine what our products are, we have to draw our circle, right? Okay. So we're going to take AG and F. F is a -1, AG is a +1, and you would get that from your periodic table that I gave you, and I'll post another periodic table on the assignment that I'm going to give you for next week. Okay. So AG plus and F minus. And then up here we have, remember we trace our numbers, right? So we have a 1 coming from here because CO3 is carbonate. So we have CO3, 2 minus, and we have Na plus. All right. Now, we don't mix here. We don't mix here because those guys are going to repel. We're going to mix diagonally. So NaF and Ag2CO3. All right. So what we're going to do is we're going to take silver. We're going to take silver plus and CO3 2 minus, and we're going to cross those. So we get Ag plus, or Ag2, so we get Ag2, and CO3 is a -1, so it's just going to be, or -2, but there's just a 1 coming down, so it's AgCO3 plus sodium plus and F minus. So Na plus F minus is sodium fluoride, NaF. Okay. Now, this does form a solid, but you have to figure out which one forms a solid and which one is not a solid. And now the next question might be, is it possible to come up with two solids? Yes, it is. You can totally do that. Okay. They can be soluble initially and then become insoluble or form a solid in the end. So let's look at this first one, Ag2CO3. Okay, Ag2CO3. So Ag is right here. All silver, lead, and mercury salts are insoluble. CO3 is right here. So because rule 3, remember this says being applied in order. Because rule 3 is higher than rule 5, this one is going to win out. But let's just say, for instance, that we skipped that one. All carbonates, oxides, sulfides, hydroxides, sulfites, chromates, and phosphates are insoluble except for CAS, SRS, BAS, and BaOH2. So what that means is that this forms a solid because of rule number 3 right here. This is exactly why I had you do that on your homework, right? So you understood what the rules were. Okay? Now, let's look at the other compound, Na and F. All Na, K plus, and NH4 compound salts are soluble. So if that's soluble, that means that NaF is a salt, and it is going to be aqueous. So this one right here is your precipitant, and this is your supernatant. Okay? All right, that's the last example I'm going to do of those. Okay? So next, we're going to move on to acid-base reactions. I'm not going to get to the calculation